All right, this video is going to be broken up into 3 parts, part 1, 2, and 3. Part 1 will cover pages 1 through 4. Part 2 will cover pages 5 through 9. And part 3 will cover pages 10 through 13. So if you were absent for any of the packet review that we've done over the last couple of weeks and you need help completing the pages that you missed, pull up the appropriate video and skip ahead to whichever problems you need, and then you can watch the video and do the packet along with me so that you can still get your full 50 points when you turn it in on Monday. Okay. All right. So for number 1, it says select all of the rational numbers. Well, before we can select rational, let's do a quick review on what is rational and irrational. So on the rational side, okay, that's over here. On the rational side, we have natural numbers. That's the N. That's just 1, 2, 3, 4 all the way up, whole numbers. And then whole numbers, the actual whole number section here adds the 0. So 0, 1, 2, 3, 4 all the way up. Integers adds the negatives and the positive whole numbers. So -1, +1 in both directions. And then when you get to the rational part, it adds fractions. So any number that can be expressed as a fraction, any stopping decimal, and any decimal that repeats. And then on the irrational side, you've got examples like pi and the square root of 2. And the reason those two are good examples of irrational is because an irrational is a decimal that goes on and on and on and on and never repeats and has no pattern. Okay, it just goes on forever and it doesn't make any sense. It doesn't have any pattern to it. So it would go on the irrational side. Well, pi is 3.141592, blah, 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 forever and ever, no repeating. And any non-perfect square, so the square root of 2, the square root of 15, the square root of 28, like anything that's not a perfect square, when you put it in the calculator to convert it to a decimal, it actually turns into a decimal that goes on and on forever and never repeats. So they all of those fit into that category of irrational numbers. And just as a reminder, if you have something like the square root of 81, well, when you reduce that down, it comes out to 9. So that would actually go in the natural spot because 9 is a natural number. So thinking of that and looking at this list, you've got 34. That's a natural number. So yes, that is rational. Pi is not rational. We know that it's in the irrational side. The square root of 75, it's not perfect. That means it's irrational. 7.912, it stops. Any decimal that stops is rational. -1 4/9, well, that can be written -13/9, and anything that can be expressed as a fraction is rational, and so that one would be irrational. 3.3333 ... Well, that means 3 repeating, and any decimal that repeats is rational, so that one does. The square root of 100 equals 10. That's a nice natural number, so that is rational. -5 is rational. It's just a negative whole number. 6.182391419 ... There's no pattern, there's no repeat, there's no stop, so that is irrational. I'm not sure why this packet does this, but this repeating thing here should be on top. It should not be on bottom. So not sure why it's like that, but let me just, so that you know what it should look like. There we go. Should look like that. Okay, same thing for here. It should not be underneath it. It should be above it. Okay, so let me put that there. So it should be above it. So you got 0.19 or 0.91 repeating, and because it repeats, it's rational. 0, of course, that's rational. It's the whole number. 6 pi. Well, I don't care if it's plus pi, times pi. It doesn't matter. It's irrational. And then 5/6, that's a nice, neat fraction. So that is rational. All right, with that in mind, number 2 is the number 7.5 rational or irrational, and then why. So you got to put your explanation in words. Well, 7.5, we know that that is a decimal that stops, right? That's an example like 0.5. So 7.5 is rational. And there's 2 good explanations, and either one of them are perfectly fine. You don't have to do both, just one or the other. One explanation is that it is a decimal that stops. The other one is that it can be expressed as a fraction. And both of those are good explanations for why something is a rational. And so just as, for example, you've got 7.5, which is 7.5, multiply and add, and you get 5 times 7 is 35, plus 1 is 36 over 5. So nice, neat fraction, nothing weird about it. So that would be a rational number. All right, place the square root of 5 on a number line below. Well, the square root of 5 is not perfect. So the only way to estimate the value of non-perfect numbers is by using the perfect numbers as a guide. So if you think of your perfect square roots, the square root of 1, the square root of 4, the square root of 9, the square root of 16, the square root of 25. Now, why did I write them above where I did on the number line? Because the square root of 25 equals 5, the square root of 16 equals 4, and so on. Okay, so those are my perfect squares. So now I need to ask myself, where does 5 fit in between those perfects? And the answer is that it fits in right here between 4 and 9. So that means it's between 2 and 3. Now you kind of have to use your own just judgment here. Is 5 really close to 1, really close to another, or is it kind of in the middle? It's closer to 4, so I'm going to shade my point here closer to 4, and that is where I would place the square root of 5 on this number line. So let me label it here. That would be where I would put the square root of 5. So if you were to make it a decimal, you would guess it would be about 2.2 or so-ish, right? Because this will probably be on a non-calculator portion of the test. If you have a calculator, you can just simply put the square root of 5, hit equals, and just so you can see how our guess was as close to the real thing, when I put that in my calculator, I get 2.23. So without a calculator, I was pretty darn close to the right answer, right? 2.2, and it was 2.23. So that was pretty good for a guess. And you can make that guess just by putting it on a number line between perfects, because we know perfects equal out to whole numbers. All right, so something just a little similar is place 5 and 5 over 7 on the number line. Well, 5 over 7, I've got a bunch of whole numbers here, so I'm going to make this a mixed fraction first. 5 goes into 7 once with 2 remaining. So 1 and 2/5. So I know it's going to be between 1 and 2, and 2/5 is not quite half, so that would be about here. So 7 over 5 would go approximately there. And again, with these, approximate is going to be good enough. Okay, you just can't be up here or down here or anything like that. So getting in the right vicinity is going to be good enough. Okay. All right. So number 5, same thing. We're placing a non-perfect on a number line. So I'm going to give me a couple of perfects here. 9, 3 times 3 is 9, 4 times 4 is 16. 5 times 5 is 25. So there's a couple of perfects. Now I'm going to ask, where does 15 fit in? Well, 15 fits in about right here. Okay. So it's between the square root of 9 and the square root of 16, which means it's between 3 and 4. And then to hone in a little bit tighter, is it really, really close to one or the other, or is it kind of in the middle? Well, this one's really close to 16, which means it's going to be kind of really close to 16 or the square root of 16, which is 4 on the number line. And let me actually put that on there. That is what I would call the square root of 15. And again, if I had to guess, if I had to make it a decimal, I would make it 3.8-ish, right? That's a guess. And let me check myself. Put the square root of 15 in my calculator and make it a decimal, and I get 3.87. So pretty good guess. All right. Number 6, put the numbers in order from least to greatest. Okay, least to greatest. And I can't really do it the way there are right now because I need to be able to compare apples and apples. And right now I've got some in radical, some in decimal, some in fraction. I can easily put everything in a decimal. So I'm going to go ahead and put everything in a decimal. And then I'm going to label it least to greatest. Well, I've really already done that over here with the 5, didn't I? I got the square root of 5 and I figured out it equaled 2.2, right? That was my estimate. So I'm going to use my estimate. So my estimate here was 2.2. And I did that by plotting that on a number line between two perfects. Negative 0.2 is already a decimal. 1/3, if you're not sure, you can do 1 divided by 3, and you end up getting 0.33 repeating. And then negative 1.0 and 1.0, those are already decimals. So now that I have everything in decimal form, it's very easy to go through and find your tiniest number all the way up to your biggest number. Well, my smallest number here, I've got 2 negatives, and the biggest negative is the deepest negative. So negative 1, I use that. And then negative 0.2, I've used that one. Now I'm done with negatives. Let's look at my positive numbers. I've got 0.3, 1, and 2.2. Well, 0.3 is definitely the next one, but I'm not going to put 0.3. I'm going to put 1/3 because that's the actual number I was asked about. And then next, I'm going to put the whole number 1. And then last, I'm going to put the square root of 5 because I estimated it to be 2.2. And that is the list of terms least to greatest. Same thing, put the numbers in order least to greatest. So I've got to do the same thing again. 1/2, I can make 0.5, 0.75, 0.7 repeating, which means it's 0.77. The square root of 2. Well, I'm going to do the same thing I did before. I'm going to give myself a number line. And I'm going to put the square root of 1 and the square root of 4. Okay, so if I plot in the middle here, that would give me the square root of 2 and the square root of 3. Those would be the ones that would fit in the middle. So my square root of 2 is going to be about right here, which is not quite half. So I'll call it 1.4. It's going to be close enough. All right, we won't need it to be any better than that as far as putting these least to greatest. So I'm going to underneath here, I'm going to put that this is 1.4, and then 2 divided by 3. When you do that, you get 0.66 repeating. So I don't have any negatives, so I go with my smallest number here, and my smallest number is 1/2. So 1/2 is my first one. Next is 0.6 repeating, which was 2/3. Notice I'm using the actual numbers they gave me, not the decimals I came up with to do a good comparison. Next, I've got 0.57 and 0.7 or 0.75 and 0.7 repeating. Well, I gave myself an extra 7 here because if I have a tie in the 7 spot, I got to go to the 10 spot here, or the 100 spot to break the tie. And so the smallest number here is 0.75 and then 0.7 repeating. So there's that one and that one. And then last is the square root of 2. And notice how my 1.4 was a good enough estimate because there wasn't anything even close to that. So it made it very easy to see that that was my largest number in the list. Number 8 should be very simple after our little explanation in our red box here. So if we look at number 8, it says for each number, check the corresponding box to tell if it is rational or irrational. Well, 900.3 is a stopped decimal, so it is rational. Square root of 99 is not perfect, so it's irrational. 6/5, nice fraction, it's rational. 2.111 ... That means one's repeating, so it's rational. Pi's in it, so we're going to go irrational. -4 is just a nice integer. It's a negative whole number. The square root of 144, well, we got to see if it's perfect first, and it is. It just equals 12, so it's rational. And then here's another example where it really should be above it, and 2.7 repeating is rational because it repeats. All right, that's page 1. Now we're going to start page 2. Page 2 is exponent rules. For exponent rules, you got to remember base, keep your base. And when you're multiplying, this is really like saying 4x's times 3x's. Well, how many x's do you have? 1, 2, 3, 4, 5, 6, 7. So that equals x to the 7th. The faster way to do it that you don't have to do this is 4 plus 3 is 7. If you can remember the plus rule, great. If you don't, just break it out into all the x's and count how many you have. Either way, you're going to get the same answer. So using that plus rule here, we got to remember that that first k does have an exponent. Every variable, every whole number has an exponent. If it's not there, it's a 1. So we've got base, keep your base. So k, we're going to keep the k. 1 plus 5 is 2, minus 1 is 5. Okay. Simplifying using the quotient rule. Well, the quotient rule is very similar to the product rule in that with the product rule, it's multiply, so you add. So the quotient rule, it's divide, so you subtract. So 5 minus 2 equals x to the 3rd. And again, there's a way to break this out and do it kind of longhand. And it's saying that x to the 5th is like writing 5x's over 2x's. And we know that when you reduce any identical term over itself, it reduces to 1. So basically those simplify to 1 and we don't need them. And we end up with 3x's, which is x to the 3rd. Same thing with the quotient rule. The one thing you have to remember here is that every base has an exponent. If it's not there, it's a 1. So 10 minus 1 equals x to the 9th. Number 5 is a power of a power. Well, power to a power is a superpower, and the way you get a superpower is by multiplying. Same thing here, power to a power is a superpower. So you do multiplying, but you got to remember to distribute. This is a base 6 and this is a base of x. Both bases have exponents, so both bases get that superpower. So x and its exponent, which is 1 times 2 is 2. And then 10, the x and its exponent is 10, and 10 times 2 is 20. If at any point while watching this video, you need to pause it, take a second to catch up, back it up a little bit. I know I'm going through this a little fast, but that's because at home, when you're watching this, you have the ability to pause. So I can go ahead and go just a little bit faster. All right, the last step here is to simplify this just a hair more. 6 squared, which means 6 times 6 is 36, x 20, and that is your final simplified answer. Rewrite using positive exponents. Well, to do this, we got to remember that every term can be written over 1. And if we want to write it with a positive exponent, remember to, if you want to change the sign, you got to change the location. So if I want to get rid of that x or that negative and write it as x to the positive third, I need to write it, instead of in the top of the fraction, I need to write it in the bottom of the fraction. And then I just fill the gap with a 1 because you can't have a blank top of a fraction. So to change the sign, you change the location. Same thing here. I'm going to give myself a fraction. I'm going to remember that this is over 1. Now, remember, you only change what has a negative exponent. The 3 still has an exponent. Everything does, but it is a positive one. So the 3 does not have a negative, so it does not move. The n does have a negative, so it moves and drops the negative. And that is the way we are able to get rid of the negative. We change the sign, we change the location. You can't just drop the sign because that changes the value of the equation. You got to make a change to kind of counteract dropping the negative, okay? Drop the negative, drop it into the fraction. All right, simplify using exponent rules. Write your answer using only positive exponents. This is a combination of 1 through 8 on this paper, right? It's kind of using everything. The first thing we're going to do is we are going to get rid of all the negative exponents by rearranging our equation. So x to the 4th doesn't need moved because it's positive. X to the negative 3rd, I need to move it because I need to get it down here to get rid of, oops, I wrote it with a negative. That's my fault. Sorry about that. Should just be x to the 3rd. If I change the location, I got to remember to drop that sign. So I needed to get rid of it. So I'm going to drop it in the bottom to drop the negative. The x to the negative 2, same thing. I need to get rid of this. So I'm going to put it up top. So I'm going to put that up here in order to get rid of the negative 2. Now it becomes, to start with, it becomes a multiplication problem. So across the top, I'm going to simplify across the top. So I'm not going to do anything to the bottom yet. X times x is x plus, remember you add your exponent. So 4 plus 2 is 6. Now it's a division problem. When it's a division problem, you subtract those exponents, and so you get x to the 3rd. So that whole big equation with all those negatives simplifies down to a nice, neat x to the 3rd power. All right, number 10, right? Yes. Simplify using the exponent rules. Write your answer using positive exponents only. That's really important. That tells us if we have a negative exponent, we got to do a flip at the bottom at the end. So anytime we see parentheses, always try to simplify that first. So inside the parentheses, we've got y times y. So we're going to keep the y, and 3 plus 5 is 8. Okay, that is just simplifying this right here. It's a multiplication problem, so we add those exponents. Now we still have to deal with that superpower. And we know that a power to a power is a superpower. So that gets written as y to the 8 times negative 2 is negative 16. And then the last step, it says positive exponents only. Well, we can write this over 1. And in order to write this with a positive exponent, we switch it to the bottom, so that it becomes y on the bottom. And of course, we fill the upper with a fraction or with a 1 because you can't have an empty numerator. All right, same thing, use simplifying using exponent rules, positive exponents only. Before we do anything, we're going to simplify across the top. So that 5x I'm going to leave alone for right now. The 10 I'm going to leave alone because there's no other number on the top to multiply it by. And then I've got base, 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 so I keep my base. It's all multiplication. So I add and I add. 3 plus 5 is 8, plus 2 is 10. Now I've got some simplifying to do, just a little bit more. 10 divided by 5 is 2. And you got 10 x's up top, 1 x on the bottom. So if I subtract that, that leaves me with 9 x's. And I don't really need to stick a 1 in the denominator. It's fine to just leave it just like that. So that would be your answer, 2x to the 9. Now we're going to change gears and we're going to look at scientific notation. So the main thing to remember about scientific notation is you need a good base. A good base, just as a reminder, a good base, okay, has to be between 1 and 9.99999. Okay, a good base has to be between 1 and 1999. So somewhere in there. So 6.5 is a good base, so that's good. Now we want to expand this. It's in scientific notation currently, and we want to expand it into standard form, which means make it just a number that you would just be used to seeing with all the zeros. So the way we do that is we take the 6.5 and we put our decimal pen or pencil right where that decimal point is. And this tells us to bounce. And because it's a positive exponent, we're going to bounce to make a big number. So 1, 2, 3, 4. Fill in the gap with zeros. And so your answer is 65,000. All right, so on number 13, it says rewrite the number in standard form. So same thing, right? We have a good base, so we're going to rewrite our good base. And this time we have a negative exponent. Negative exponents always mean teeny tiny numbers. So we're going to have a really teeny tiny decimal here. So that tells us that we put our pencil right where the decimal point currently is, and we bounce to make a teeny tiny number 6 times. So 1, 2, 3, 4, 5, 6. Fill in the gap with zeros. So our answer is 0.5 zeros. 1, 2, 3, 4, 5, and then 9, 3, 4. Again, just as a reminder, positive exponents give you big numbers. Negative exponents give you teeny tiny numbers. And that's a teeny tiny number because that is way less than 1. Okay. Same principle applies when you're going the other way. Now you have a standard number and you want to rewrite it in scientific notation. So you put the decimal where it is, and if it's not there, it's always at the end. And you bounce until you have a good base. So 1, 2, 3, 4, 5. I can't stop here because that would give me 89, and 89 is too big. 6, that's my 6th bounce. If I leave it there, it gives me 8.9, and 8.9 is between 1 and 9.9, so that's a good base. So I'm going to leave it there, times the base 10, and then my exponent, because it's a big number, is going to be positive, and it's how many times did I have to bounce? 1, 2, 3, 4, 5, 6, so it's 10 to the 6. Okay, big numbers, positive exponents. Now I'm going to rewrite this one in scientific notation. I'm going to put my decimal where it's at. It was already there, so I'm going to put it there, and I'm going to bounce 1, 2. Now I can't stop here because that would be 0.76, and that's less than 1. So I'm going to do a third bounce to go right there at 7.6. So that's a good base because it's between 1 and 9.9 times 10 to the, now it's a teeny tiny number, so I'm going to have a negative exponent. How many bounces? 1, 2, 3. So this would be the scientific notation for that standard number. Don't try to memorize left and right. It's just easiest to always remember big numbers, positive, teeny tiny numbers, negative exponents, no matter which way you're going. All right, which numbers are written in scientific notation? So really we want to look at our bases here and make sure our bases are good bases. So for A, our base is 9.5. That decimal point is in the right spot. So yes, this one is proper scientific notation. 0.01, well, that's way less than 1, right? So that base is not a good base. So I'm going to strike through that one. That is not a good scientific notation. 7 times 10 to the negative 4. Well, it's really 7.0, which we know is good. That's between 1 and 9. So yes, that's a good base. 7 is between 1 and 9.9. 35, definitely way too high. It would need to be 3.5, and it's not. So 35 is way too big of a base. It's way higher than 9.9. So I'm going to strike through that one. And then 65.4, nope, it would have to go here for it to work, and 65 is definitely too big of a number to be a good base. So our only options here are A and C. Which number is bigger? If it doesn't jump right out at you, just put them both in standard form and then compare. It's kind of easier that way anyway. So 3.5, if I bounce 7 to make it giant, 1, 2, 3, 4, 5, 6, 7, add all your zeros. On this side, I'm going to take 9.5, right? 9.5, and I'm going to bounce it twice to make it bigger. Obviously, this number is way bigger than 9.5 times 10 to the second. Like I said, if it doesn't jump right out at you, just put them both in standard form, and it's really easy to compare in standard form. All right, this is page 3. Page 3 is solving equations. Like I said, I'm going to kind of run through these fast, pause the video, back it up. That way you can kind of take your time if you need to. My goal is to solve for x, right? That's my ultimate goal. So the first thing I want to do is move any extra numbers that are not tied in with a fraction or with multiplication. Kind of there, I always say that they're not attached as tightly. So that would be that -9. It's just kind of dangling there with a plus or minus sign. It's very easy to snap off. So the opposite of -9 is +9. Whatever I do to one side of the equal sign, I always do to the other because I want to keep my wall balanced. And when that is gone, I'm left with x over 3 equals 13, -13 plus 9 is -4. Now that x is tied in a fraction with the 3, and fractions are division. The opposite of division is multiplication. You always do the opposite to break it loose. And really, we don't think of it like this, but it's 3 over 1. But what ends up happening is these two cross cancel, and we're left with x equals -4 times 3 is -12. And if you plug -12 back up into the equation, you get -12 divided by 3, which is -4, and -4 plus -9 is -13, so it checks out. All right, number 2 is a little different. Notice in number 1 that -9 was not tied in a fraction, and in this case, the +8 is tied in a fraction, so we can't really do anything with it just yet. First, we got to get rid of the fraction. Again, if we get rid of a fraction, fractions are division. We're going to do multiplication because you always do the opposite. Don't know why I wrote a 5. And you multiply by the denominator. And when you do that, the denominator cancels out with that 4, and you're left with n plus 8 equals 8 times 4 is 32. And now we just have to move that 8, and it's attached with addition. So I break it loose with subtraction. Remember my wall, whatever I do to one side, I do to the other to keep my wall balanced. And I'm left with n equals 24. And again, you could plug 24 back into your equation and you would get 8 equals 8. All right, same thing here. You've got the -10 in, they're multiplied, they're really tightly bound right now. So let's snap off the 7 because it's easier to move. It's not tied in with any tight multiplication or division. So the opposite of -7 is +7. Whatever I do to one side of the wall, I always do to the other to keep my wall balanced. That leaves me -10n equals 63 plus 7 is 70. Now I want to break that 10 and that n apart, and they're attached with multiplication. So anytime you want to break it loose, you always do the opposite. The opposite of multiplication is division. So I'm going to divide both sides by -10. And the reason I want to divide by -10 is because -10 divided by -10 is 1. And really, we don't ever write it, but that's 1n, and that's solving for n. That's getting the n by itself. And then 70 divided by -10 is -7. And again, you can plug -7 in and test, you'll get 63 equals 63. All right, for number 4, anytime we see parentheses, we always need to think distribution first. So when I distribute that, that gives me -3 equals 3x plus, well, not plus. -6 times -6 times -x is -6x, and 6 times 3 is 18. Now, before I start thinking about my wall, because here's my wall, before I start thinking about moving things left and right around the wall, I need to look and see, is there anything on the same side of the wall that I can write in a combined manner? So 3x and -6x are already together on the wall. Notice what I don't do. I don't minus 3x and minus 3x. Look at your wall. I've done -3x twice on the same side of the wall. I have thrown my whole equation off balance. So I do not want to do that. All I want to do is think, if I have 3 apples minus 6 apples, I could write that more combined as -3 apples or -3x. The rest of the equation I'm going to leave just like it was. So -3 equals, right here, I combined, right here, I combined 3x and -6x. They were already together in the same side of the wall. I combined them to -3x. Now I can start working to get my x by itself. And again, what's kind of attached loosely is this +18. I'm going to snap it off there with a -18. Do it on both sides of the wall. Because I am actually wanting to get rid of it on this side, not just combine it, I am going to do it on both sides of the wall. And when I do that, +18 and -18 go away, and I'm left with -3x. And on this side, I got to simplify. -3 minus 18 is -21. Now I got to look at my x again. What's attached and how's it attached? Well, it's a 3 and it's attached by multiplication. I always do the opposite to break it loose. Opposite of multiplication is division. -3 and -3 equal a 1. So it's just 1x or just x. And -21 divided by -3 is +7. All right, number 5. If you want to pause this video for a second, see if you can work this on your own and then unpause it. That'd give you a good idea if you're kind of tracking. All right, so r/6, that's trapped in a fraction. I'm going to deal with that last. So the first thing I want to do is I want to snap off that 3. It's a positive, so I'm going to do -3. Here's my wall. Whatever I do to one side, I do to the other. And so my 3 and -3 zero out or are gone now, and I'm left with r/6 equals -2 and then -3 deeper. Think if you dig a hole too deep, then you dig 3 feet deeper, you are -5 in the ground. Now the r is trapped in a fraction. Fractions are division. I'm going to do the opposite, which is multiplication. Always multiply by the denominator. Whatever I do to one side, I do to the other to keep my wall balanced. I don't ever want my wall tipping. All right, so x and x reduced to a 1, giving me r equals -5 times 6 is -30. All right, same thing with number 6. If you want to pause the video, try it and see what you get, and then unpause the video and see if you were right. All right, so I'm going to get rid of these parentheses by distributing first. So when I distribute that -2 to the x, I get -2x. Distribution means multiplication. When I multiply the -2 times 11, I get -22 equals -18. Nothing to combine together, right? I can't combine x and 22 because one has an x and one doesn't. So I'm going to get my wall there. And I always snap off the easy plus minus first. It's a -22. Opposite of that is +22. Whatever I do to one side of the wall, I do to the other. Keep my balance. That's now gone. I'm left with this -2x, -18 plus 22. Signs don't match. Subtract and take the sign of the bigger. Again, I've got 2 times x multiplication, so I'm going to break it loose with division. And that gives me x equals -2. Number 7, is 5x or 5 equals x a solution to the equation? And they give you the equation there. Prove your answer by substituting and solving. So here's my equation. Okay, there's my equation. And everywhere where I see an x, I'm going to put a 5. So right here, I'm going to put a 5. Right here, I'm going to put a 5. So I'm going to rewrite my equation down here with those 5s in place. So 3 times 5 minus 4 equals 5 plus 1. I've substituted x into the equation. Everywhere where I saw an x, I put a 5. Okay, now 3 times 5 is 15 minus 4. 5 plus 1 is 6. 15 minus 4 is 11. Does 11 equal 6? No, it does not. Therefore, no. X minus 5 or x equals 5 is not a solution, and it says prove your answer by substituting, and that's exactly what we did. All right, if you want to pause the video, you can try 8. It's the same principle. They tell you to check to see if y equals 11 is a solution to that equation. That means everywhere where I see a y, I'm going to substitute in an 11. So let me rewrite that. 11 plus 5 equals 2 times 11 minus 3. Now, there's a couple of different ways you can do this. I'm going to go ahead. 11 plus 5 is 16. I'm going to go ahead and combine inside my parentheses first because they're like terms. So 11 minus 3 is 8. Now I'll do the multiplication. 2 times 8 is 16. And it checks out. Yes, it is a solution. Now, if you had gotten to this point right here, 11 plus 5 equals 2, 11 minus 3. If you wanted to distribute first, I'll show you, you can. Either way works. 2 times 11 is 22. 2 times negative 3 is negative 6. 11 plus 5 is 16. 22 minus 6 is also 16. So notice you get the exact same answer either way. Okay, so whichever way works for you. If they're like terms in the parentheses, it's usually easier to subtract or to combine inside the parentheses first, but either way works. All right, number 9, same thing. X equals 1/2, wants to know if it's a solution. So everywhere where I see an X, I'm going to put a 1/2. So I'm going to put a 1/2 here, and I'm going to put a 1/2 here. 2 times 1/2 plus 5, does it equal negative 1/2 plus 1? So let's do a little bit of reducing here. 2 times 1/2 or half of 2 is 1. And inside those parentheses, 1 plus 1/2 is 1.5 or 1.5. Either way, it doesn't matter. 1 plus 5 is 6. Negative 1.5, 1.5 or 1.5, it doesn't matter. Do they equal each other? No, they do not. So no, X is not a solution, and we proved it by substituting and solving. All right, last page for this video is number of solutions. So we talked about this earlier last week in class. Your possible answers here are 1 solution, and then the 2 special cases are no solution and infinite. Those are the 2 special cases. And remember, for the 2 special cases to happen, something special has to happen on your equation. On each side of the equation, for both of these, you need something identical on the variable. 3x equals 3x, 10x equals 10x, doesn't matter. But for the special cases to happen, you need your variables to be identical on both sides. So let's look at number 1. We've got 3x plus 5 equals 2x minus 5 plus x. Well, the first thing that should stand out is you got 2 x's on the same side of the equation. So before we do anything, let's combine those to get it a little bit simpler to answer. So 3x plus 5 equals, now 2x and 1x is 3x, and then minus 5. Now notice this is a special case because notice what happens. If I were to subtract 3x to try to get it over on the left, what happens when I subtract 3x from here? Because they're identical, they cancel out on both sides. And what I'm left with is 5 equals negative 5. So is that true? No, it is not. So between no solution and infinite, what do you think it is when it's not true? Is it true? No, therefore it is no solution. All right, let's look at number 2. Before we do anything, we got to distribute. So we've got 4 times x is 4x, and 4 times 1 is 4. And if you notice, you've got identical things on both sides of the equation. Again, what happens? 4x minus 4x minus 4x, they go away. What are you left with? 4 equals 4. Is that true? Yes, it is. So it is, of the 2 special cases, right? These are your 2 special cases. Infinite is when you have a true statement. So this would be infinite solutions. The other way you might see that written is all real numbers. Both of those mean the same thing, okay? All real numbers. Either one of those is fine. But how many solutions are there? Well, there's an infinite number, okay? Because every single real number in the real number system would work. Now, these are examples of 2 special cases. Notice in both cases, the variables were identical on both sides. So let's look at number 3, 2x plus 7, 3x plus 7. Right off the bat, you should see that it is not a special case because 3x and 2x are not identical, which means if it's not one of the 2 special cases, what does it have to be? It has to be 1 solution. That's the only option. So we know this is a 1 solution. We know that's the answer. But I'm going to prove it. So let's go ahead and solve this by, let me get rid of that line that I put there. All right, so how would we solve this? Well, we got to get all of our x's on one side and all of our numbers on the other. So if I subtract 3x over and I subtract 3x over, I get negative 1x plus 7. Remember my equal sign, equals, that's now gone, and I'm left with 7. Now I'm going to subtract 7 because I want to get variables to the left, numbers to the right. So I mean, this is just like a one step at a time. You just chisel away at it. Negative 1x equals 7 minus 7 is 0. And don't let that 0 trip you up. It's not a no solution. It just means that when you divide negative 1 by both sides, you get x equals 0. That's still one solution because 0 is a number in the real number system. So was it one solution? Like I said, yes, it was. The solution was x equals 0. Anytime you have variables that do not match, identical on both sides, it has to be one solution. All right, on this one, we're going to distribute before we go any further so we can compare. 3 times 2x is 6x, 3 times 5 is 15. All right, what do we notice? 6x and 6x. So when we minus 6x and minus 6x, they're going to go away, leaving us 15 equals 20. Is that true? No, so it is no solution. Special case. Here you see 4x and 4x, but don't jump the gun. You got to combine like terms if you can. So we've got a 4x and a negative 1x that have to be written together first. So 4x minus 1x is 3x plus 5 equals 4x minus 5. Well, what happens if I, I'll take my x's over to the right this time because it doesn't really matter. If I pull my x's off of this side, whatever I do to one side, I got to do to the other. That gives me 5 equals 1x minus 5. And if I add 5 to both sides to get all my numbers, all my whole numbers together on one side of the equation, that's gone. And I'm left with 1x or just x, and 5 plus 5 is 10. So was I right? Yes, I knew it was one solution before I even did an ounce of math. And the way I knew that was at this step right here, 3x and 4x were not identical. So that means they weren't going to cancel each other out. So it wasn't one of the special cases. All right, this box should be very easy to do with the little trick that I just showed you about matching x's. So on that first example, 3x and 3x are identical. So they're going to cancel out, leaving you 5 equals 4. Is that true? No, so it's no solution. 2x and 3x don't cancel out. The only possible option is one solution. 3x and 3x cancel each other out. You're left with 5 equals, well, it doesn't equal 5, right? So it can't be infinite. It equals 0. And is that true? No, so that's no solution. And then 3x and 3x are identical, and you're left with 5 equals 5. That is a true statement, so it is infinite. All right. This is our last few here. All right, Danny says that the equation 4x plus 3 equals 3x plus 3, parentheses 3x plus 3. He says it has no solution because when he solves it, he gets 4x equals 3. 2 parts to this. Is Danny correct? And then why or why not? So first, let's look and see if Danny is correct. So let's take the equation that Danny has. He has 4x plus 3 equals 3 times x plus 3. And we know we got to distribute before we do anything. And so we get 4x plus 3 equals 3x plus 3 times 3 is 9. Now, right off the bat, you can see that Danny is not correct. Danny said it was no solution. And we can see that we have a 4x and a 3x that are not going to cancel each other out. So we can just say, is Danny correct? No. Okay. No, it is one solution. Okay. This is the y. No. It is one solution. Okay. And let's go ahead, since he gave us this as an example, let's give him the real answer. So I'm going to subtract 3x, and whatever I do to one side of the wall, I do to the other. Keep my wall balanced. Got a 9 left over on the right. Over here, I have 4x minus 3x, which is 1x, or you can just write x plus 3. And now I got my variables to the left, so I want to get my numbers to the right. So I'm going to subtract 3 and subtract 3. And 3 minus 3 is 0, leaving me x. 9 minus 3 is 6. So no, Danny is not correct. It's one solution, not no solution, because x equals 6. So he gave you this false claim, you give him the real claim. Okay? Number 8, we are going to create or fill in the blank to create an equation with, now this is important to pay attention to, infinite solutions. So think about what we need for infinite solutions. We need matching variables and we need matching other number, right? Matching variable and matching other number. So let's distribute first. So 10 times x is 10x and 10 times -2 is -20 equals, they give us 10x. We got to figure out what to put in this blank to make it match or to make it infinite. Now remember what has to happen with infinite. 10x and 10x have to cancel out, and they do. And for infinite, what has to happen? This has to match this side, right? So we're going to put a -20 in here because for it to be infinite, our 10x and 10x have to cancel out, and then what's left behind has to match. All right, so we created an infinite. Now this last one is create a no solution equation, right? This one is a no solution equation. So think about what has to happen. On no solution equations, it's still a special case. Our variables, in this case y's, have to be identical on both sides. And then we have to make sure that our numbers are not the same because we need it to be not equal to each other to be no solution. So the first thing I'm going to do is distribute, and that gives me 2y. 2 times 5 is 10 equals something minus 10. Well, think about what has to happen for no solution. Do it in the highlighter here. My 2y has to be identical to my what? My 2y. So the only possible solution here is a 2y. Because if I have 2y and 2y, they cancel out, and then I'm left with +10 and -10. That is not true, so I created a no solution. Okay, that is the end of the first video. This is part 1, page 1 through 4. The next video will be pages 5 through 9, and then the final video will be pages 10 through 13. So let me know if you have any questions, and this is due on Monday before we start ILearn. Have a great weekend.